think what might be better personally is to show you guys, to show everyone that is, how to graph it using Desmos. Okay. And that's actually where this link is supposed to take you to. And actually, I found it online. It's actually, I do know how to make it. But there's actually something in Desmos that you can use to graph it. But before we get to that, let me just show you this. It actually turns out that the graph of a normal distribution is the graph of this curve, of this function. You know, we did talk about functions a little bit, but if you were to graph this function in the Cartesian plane, in the plane, you know, like in Desmos or something, you would get the normal curve. I know it looks kind of nasty. EXP, that's just fancy notation for e raised. You know, we have seen e raised to the x. We have seen that. It's just that here the exponent would be very complicated. So what people do, instead of using this, e to the x, they came up with this notation, which means the same thing. So really, this is e raised to everything in parentheses. B is the mean. A is the standard deviation. So really, I guess A has to be positive, not A can't be 0. So but I'll show you shortly in the Desmos calculator. This is actually what you would graph to get the normal distribution curve. I mean, you could use e raised to the exponent, but people also use this for notational convenience. B is the mean, A is the standard deviation. In other words, you could fill in different numbers for B and A, and you would get the mean, B, A is standard deviation, whatever that is. Okay. And let me just say this also. I'm using these letters, but what people generally use in the math world, I'm sure elsewhere too, for the mean, people use a Greek letter, this letter. Here, wait, they can't see that. This letter they use for the mean, that's what usually people use, this Greek letter called mu. I tried to write out how you pronounce it. I don't know if I was successful. It looks like a U, but it has like an extra tail here. It's actually a Greek letter called mu. That's for the mean, for a normal distribution. And for the standard deviation, people use this Greek letter called sigma. Sigma. It looks like a, what do you call it? It looks like an O, a lowercase o, but again, it has this extra tail on top. It's just notation people use. I mean, I'm sticking with A and B now, but this is just notation people use. That's all. So let me go to Desmos. And, whoop, not yet. Go back to Desmos then. I mean, if you were to click on this link, although I have it, it's in your notes also. If you were to click on that, or like, you know, copy it into your browser, you would end up at, let me see if I can find it, at this, not this. Let me get rid of that. You would end up at something like this. Wait, no, you guys, let me share that with you guys. You would end up with something like this. I mean, instead of Adam, it would be like sign in, create an account, because it doesn't, if you don't have an account, that is. But this is what you would get. Okay. It says up here, area under the curve is probability. You, for now, just ignore that. We'll get to that later, I think. But this is what you would get to. And you could change these values of A and B, as you can see. You know, you have like these little, what do they call it, sliders, I think. That can actually shift the graph. So for instance, if I change B, which is the mean, right? Well, there we go. You know, I could change B. I could click on the slider and move it, and you could see that the graph will shift. So this is where the mean is. It's also where the peak of the graph is. You can see the graph looks like a hill, right? And that's where the graph is, the peak. So here's where the mean is 0. Here the mean is at 3. Here it's at -4, and so on. Okay. A is the standard deviation, though. So A instead is the standard deviation, okay? So on the next slide in the notes, I actually have the mean as 5 and the standard deviation is 2. Let me get to that. But this is what the graph would look like. So the peak here, the top that is, okay, that's where the mean is. And the mode and the median. All right. So that's where this is. Let me just get to these slides. Let's see. Okay. But now let me show you this though. Let's see what happens though. Okay, this is in the notes, but let's see what happens if we vary the standard deviation. So just to make it consistent, let me get the mean at 0. Okay, so everyone can see this. Watch what happens when we change the standard deviation. Okay, actually, let me see if this will work. No, let me just do it this way. So you can't have it at 0, but if you increase it, make it bigger, you can see that the graph is becoming flatter. And how do I say that? I guess it's becoming more, yeah, it's becoming flatter. Basically, if you increase the standard deviation, right, what happens is, remember, the data gets more widespread. You know, it spreads out more. So if we increase, so if we start from here, right, if we increase the data, see, it's increasing, you can see the graph gets flatter and flatter, mostly because the data is getting more widespread. But instead, if we made it smaller, wait, hold on, no, I thought it here. But instead, if we decrease it, you can hopefully, let me see, can everyone see? Yeah, everyone can see what I'm doing. If you were to decrease the standard deviation, what's happening now is that the data is getting more clustered around the mean. And you can see the peak is going up. The data is more concentrated at the mean. So with a normal distribution, the bigger the standard deviation, the more spread out the data is, the flatter the graph looks. Whereas if it's smaller, okay, then it's more clustered around the center. It's more clustered than around the center. Okay, let me just get back to the notes. Here we go. Okay. So again, you can see here that I just wrote down some of the things that we saw. You know, the smaller it is, the narrower the graph will look. Remember, it has to be positive also, the standard deviation. Doesn't make sense to have a negative standard deviation. And the higher the peak will be. Okay? The higher it will be. You know, it's more clustered around the mean. That's what happens when it's smaller, the standard deviation. The bigger it is, the flatter the graph looks, mostly because the data is getting spread out more. And as I said also, the peak, you know, the top of the hill that is, that's where it's where the mean occurs, okay? So this is when the mean is 5 and standard deviation 2. Okay. And again, that's where it occurs. So if you vary the mean, you know, you're going to shift the graph horizontally. Okay. All right. Are there any questions about that? Let me just keep going. All right. Okay, so now there is actually, let me see, I don't know if I can get the textbook, but I'm going to try. See if I can get the textbook, because the textbook has a much better picture than I can draw. So let me see if I can find it. Okay, chapter 12. There it is. Let me see what page it's on, because no. Oh, here we go. Here, this is good. All right, let me I don't know if I can share. Let me see if I can share that. I mean, you could download it anyway from the homework, from the website where the homework is. But what basically they're going to show you is visually that most of the data is going to be within one standard deviation from the mean. Excuse me, not most of it, 68% of it will be. And as I said before, also, if you go further out, you will get more data. But once you go beyond 3 standard deviations, you're not really going to get much more data than this. This is what they call the empirical rule, excuse me. So basically, most of the data, again, is concentrated near the mean. If you go 1 standard deviation out, you're going to only have about 68% of the data. But if you go another standard deviation, so that is you went 2 out from the mean, then you'll get about 95%. Okay? Then you'll get about 95%. Here it comes. Yep, here it is. This is in the textbook, but hopefully you can see it anyway. Hopefully you can see it. And then as you can see also, if you go out 3 standard deviations, you can see that they're using that sigma for standard deviation. You get about 99.7%. Most of the data then is within 3 standard deviations. So I'm pretty confident that doesn't happen with other distributions, but that's one of the really nice things about the normal distribution. It's one of the really cool properties about it. You know, it's what they call the empirical rule. So basically, anything beyond 3 standard deviations from the mean, whether to the left or right, it's going to get pretty rare, is what they're saying. We have the so-called empirical rule. How do you prove that? I honestly don't know. I think it takes a lot of, what do you call it? A lot of calculus, I'm thinking. But that's a different story. All right. Okay, let me just see how much more notes. Okay, I mean, there were some examples I was going to, I don't want to rush. Well, let me just do one, I guess. So let me do one example. I know I'm bouncing around like this, I know. But that's okay. Remember, the textbook you could download for free from the book. I mean, I'm sure you knew that by now. At least I hope so. But let's say, for instance, you know, someone gave an exam, they recorded the scores, and they discovered that the scores were normally distributed, and the mean was 8, and the standard deviation was 2. Okay, so the mean is 8 in particular. So if you add a standard deviation, you know, that's the same as adding 2, you're going to get 10. If you subtract, you get 8 minus 2, which is 6. Add 2 standard deviations, right? You're adding 2 times 2, which is the same as adding 4, and you get 12. Subtract 2 standard deviations, you're subtracting 4, and you get 4. If you add 3 of them, you get 6. Subtract 3, you end up with 2. So let me see. So basically what they're saying is, on that exam, this is the normal distribution, 68% of the scores are between 6 and 10. So 68% of the students scored between 6 and 10 on this exam. I think I better go through this one as well. I'll go through this one as well again next time, because it looks like we have about 30 seconds left. But basically, it's just telling you where most of the scores are going to be. That's all. They're going to be centered around 8, which is the mean. So I think we'll go more into this next time, so I'm going to stop here. Okay? So that stuff, so